Hello everyone, welcome to our course on design of concrete structures. In this first lecture, we will try to understand what structural design really means. Also, we will try to recall some of the basic concrete terminologies and see why steel reinforcement is so important as well as RCC is considered. So let us begin. So let us start by understanding what really structural design is, or in other words, let us try to understand what is the basic difference between structural analysis and structural design. In this slide, you can see two pictures. On the left side, we have a simple RCC frame. So in normal case, in every building, we will be having some people or something kept on the structures, right? So these structures will act as an external load on some of the members. So for example, here you can see these peoples are actually standing on the slab. So when this load act on the slab, some sort of things will happen inside the slab. Am I right? So basically, when we consider structural analysis, our focus will be to evaluate what sort of force is actually generated inside a structural member. Whereas when you move on to the structural design, so once we have an idea about what sort of force is actually acting in a member, we have to ensure, as an engineer, we have to ensure that the structure is safe and it can safely carry these loads. So for that, these members will require some dimension, some minimum dimension as well as some amount of reinforcement. A structural designer will do this thing. That is, he will decide how much dimension to be provided for each elements as well as how much reinforcement should be provided in these elements so that the force which is acting inside the structure can be safely carried without any problem. So that is the basic difference between structural analysis and design. So in structural analysis, we will be more focused on what force and moments act inside the member. Whereas when you come to structural design, we will know the forces and we will finalize how much thick or how much wide or how much steel to be provided in these members so that it will be safe. Both these steps are actually essential. But design is where we translate the numbers into drawing. So once we complete the design, we will be providing some drawings to the field. By the end of this course, you should be able to predict the behavior of basic structural elements like beams, columns, foundation, etc. when they are subjected to flexural shear, compression and torsion actions. You will be also able to understand the provisions given in Indian Standard Code for Design, which is Indian Standard 456-2000, and you will be able to use the same for designing basic structural elements. You will also have a basic exposure on the earthquake resistant design and the detailing recommendations given in some of the Indian standards. So for this course, I would suggest this textbook as your reference. So I recommend the textbook by Devadas Menon sir and Unikrishnan Pillai for conceptual clarity. Whereas if you take this book like from Punmaya, you have a lot of solved examples provided in that. And when you come to Varghese, it is more good for limit state, understanding the limit state philosophies. So, and one more thing I would like to stress here is so whenever you do problems on design of concrete structures, you should have your Indian Standard 456 open with you. Let us start with the materials used for making RCC concrete. Let us start with the materials used for making reinforced concrete. So we know in a broader perspective, the main materials in RCC are concrete and steel. So let's start with the first material, which is concrete. So you might have already heard about the term plain cement concrete or PCC. So what is that? PCC is nothing other than a mixture of cement, fine aggregate, coarse aggregate and water. When we consider this material, that is PCC, we can see that this material is very strong when it is subjected to compression. But on the other hand, if we are applying a tensile force or if we are providing a tensile stress on this material, it is very weak. It will easily get damaged. So this slide actually shows a test which is conducted on plain cement concrete beam. So you can see one beam is kept in universal testing machine. It is supported at the bottom and the load is provided at 2 points on the top. So after some time you can see when the load is increased, the beam is getting damaged. But one thing that we have to note here is like you can see the damage actually started from the bottom part. The cracking started from the bottom and it have grown towards the top side. Can be the reason for that. So let us analyze this. So when we subject this beam to some load, what will happen? This beam will have a tendency to get bent. Okay, it will be subjected to flexure. So when this beam bends, what will happen is like the fibers at the bottom will be experiencing some sort of tension, whereas the fibers that is coming on the top will be experiencing compression. And we have already seen that concrete is weak in tension. That is why initially the crack started forming from the bottom fiber, and once a small crack is formed, when we increase the load, it will easily get grown into a larger crack and finally the damage occurs. So let's take one more example. So here in the bottom figure, you can see a concrete cylinder is subjected to split tensile strength. So here what we do is like we are actually applying a compressive load. So we have seen the concrete is very good in taking up compression. So we are keeping the cylinder like this and we are applying the compressive load in the vertical direction. But after some time you can see the concrete easily fails and the plane of failure is vertical. This vertical, the failure actually happened through the vertical plane. What can be the reason for this? So when you see the loading, when we apply this compressive load in the vertical direction, due to Poisson's effect, what will happen is like in the perpendicular direction, we will be experiencing a tensile force. So that tension is actually causing the final failure. That is why the plane where failure occurred was the vertical plane. Now, let's one more time consider the flexure action. So here you can see one beam is there and we have applied a UDL and some point loads on the beam. So what will happen to this beam? This beam will be subjected to flexure and it will undergo bending. So as we earlier explained, when a beam is subjected to flexure, what will happen? The top fibers will experience compression, whereas the bottom fibers will experience tension. So if you observe the stresses that is formed inside the beam, you can see on the top portion, that is the portion above the neutral axis, will be experiencing compressive stress, whereas the portion which is below the neutral axis will be experiencing tensile stresses. So what will happen? We already know concrete is very weak in tension. So there is high probability that the bottom part will easily get damaged. So what can we actually do in this case? So an easy solution was that to use some other material which is good in taking up tension at these parts where we are actually experiencing the tensile stress. That is how we came with the term called as reinforced cement concrete. So here what we actually do is like, now we have seen when a member is subjected to flexure, the top part is experiencing compression and the bottom part is experiencing tensile stresses. So we will be providing a material. In this case, it will be steel because steel is very good in taking up tension as well as compression. So in the tensile zone, what we do is we will be providing a steel bar so that when this beam is undergoing flexure, what will happen? The compression force or the compressive stress which is coming on top will be taken by the concrete, whereas when the tensile stress is found at the bottom of the beam, what will happen? This steel reinforcement will take up all that tensile stresses. So as a whole, these two materials will act together and it can carry a large amount of load.